Okay, sorry for the time today.
Hello everyone, I'm Cheng. I'm currently a final year PhD student in information system from Boston University. Today I'm very happy to be here to talk about our project, InnoVAE, Generative AI for Patents and Innovation Firms. This is a joint project with Professor Dr. Li from BU and Prasanna Tempe from Wharton. So today our topic is generally about generative AI. So what is really generative AI? So mathematically speaking, it is nothing but an algorithm that generates objects by modeling its distribution. So the variable S can be anything, like the text, the images, the patterns, the job descriptions. So in short words, they generate things by modeling the probability distribution. So, but another side of the story is that generative AI also have the potential to be representation models. The simple idea, the intuition behind this is that to generate an object, the generative AI inherently learn to capture and represent the underlying structure of the data on which they are trained on. Hence, generative AI should have the potential to first map out the object space and provide deeper insights. For example, we have two objects. We can look in the latent space and see how they are different with each other. And also, we can create or augment new objects so that we want the certain objects to be more aligned with a certain kind of business concept or business objectives. But unfortunately, not all generative AI are created equal. So we have nowadays the most popular one are large language model, which models the generation of the languages. So this is a nice visual that's talking about the three categories of the generative AI. We have the encoder-only model on the very left branch, which is essentially more focused on getting the representation embedding of the input sentences. We have an encoder-decoder model, which is back in years the commonly used for sequence-to-sequence tasks, such as language translation and speech recognition. And on the right branch, which is really exciting nowadays, is the decoder model that powers all the large language models like ChatGPT and Google Sparks. So generally, the decoder model they serve as like an autoregressive, meaning that they work by learning to predict the next words in a relatively long context. But however, those kind of decoder model are generally not appropriate for mapping the representation. To give an example to about what I mean here, so actually OpenAI recently have the study that's trying to explain the neurons in the decoder-only model, specific about the GPT-2. So what they are doing is that they ask a more advanced version of the large language model, the GPT-4, to look into the activation of the layer in the large language model, GPT-2, and write explanations for the behavior of those neurons. So although this kind of approach gave some good explanation about how each of the tens billions of neurons work, but they also found that there are many neurons that have the complex behavior that's really impossible for people or even for machines to describe succinctly. So our research question now is, can we really harness the generative AI to learn like or interpretable representation? And the second question is, okay, if I got this kind of representation, how we are going to use it? So to address this research question, we are applying for a different model. It's InnoVAE, which is a variation of autoencoder for a transformer for patents. So basically, it is an encoder and a decoder model, but we add some variational penalized term that encourage the disentanglement in their learned representation, and I will talk about that later. So specifically, this is how it works. First, our model maps the real-world objects, such as a patent, into a low-dimensional vector space. and then so that each dimension are extracted so that they are distinct and uncorrelated. And statistically, they are constructed to be more statistically independent, and the movement in the space rendered meaningful and understandable. So let me give a more intuitive example about what does this disentanglement really mean. For example, let's have the machine learning algorithm that do nothing but looking at the 1 million sample of cylinders. So we asked this machine learning algorithm to say, let me find a disentangled representation space. So in this case, disentangled representation algorithm will just find that, okay, for the cylinders, we can find that there are like 2 latent factors that can uniquely specify the dimension of the cylinder, which is the radius and the height. Because they are independent to each other and they are also in a way very interpretable to human. So if we kind of expand the same idea from the cylinder on patterns, we can similarly develop like an algorithm that given, like here we give you a bunch of patterns. The disentangled representation algorithm will just find the factors innovation that compromise a group of patterns. For example, we might find the patterns like AI patterns might contain like factors such as the security, such as the human-computer interaction, etc., etc. So here's like an overview of our model. So our InnoVAE basically mapped the patent text, like the claims, into an interpretable spatial representation of the firm's innovative activity. And then we call this latest factors the innovation space. Within this space, we can move the point in this space and explore and make exploration into the patent and the firm's innovation activity. And this model is not really possible if we're using like a traditional disentangled or dimension reduction algorithm. So at the right side of the slides, I show I select so this is the result come from our the AI patents, and I select the 2 innovation factors, the document processing and human-computer interface, and we can see that we can actually map the firm's patent in the space and kind of compare and contrast each firm's innovation space within these 2 dimensions. So you might still ask, why is this important? What's like the disentangled representation can enable? What kind of task I need to do? So there are several ways this kind of disentangled representation can do. First, this might help answer the question, what could you get if you combine pattern A and pattern B? This might be used for automated creating of the pattern by simply combining 2 existing inventions. And the second kind of task is that we can actually use the method to measure how unusual a pattern is with specific to the specific technological factor. For example, we can look into like the iPod interface and see how friendly it is, compare what is exceptionality it is within the user interface perspective. And we can this will also help answer the question like what information factors will increase or decrease over time. And we can also rank the companies in the specific technological factors. And another thing is that if I am a firm A, what innovation I need to do to boost up my innovation so that I can beat a certain incumbent company, and how do firms move in the innovation space over time, and how does that correlate to some performances. And we can also measure the innovation activity after a certain shock, etc., etc. So let me give you an example. So in this project, we run the US patent on the AI and the computing systems, which cover like 3 decades of patents. So the famous patents are including this sample or like the PageRank algorithm that used to power the Google search engine, and also the multi-touch patent that is used in iPhone. So here are some of the innovation factors we have extracted from the US AI patents. We found a certain dimensions such as the finance transactions, automation control. We also find things like medicine, connectivity. We also find HCI, etc., etc. So here's a one application we can use. For example, we can what we can do is that we can randomly take two patents in the space and merge it and see what will be the combinational innovation that come out of the two patents. For example, let's say we have a patent that uses a search engine to search the multimedia data, and we have another patent that's for rapid updating of the private information. So let's take a guess what kind of innovation will this be generated. So according to the firm, according to the algorithm, the most close to patent that is that combine these two patents is about the process for protection against the fraudulent use of smart cards. So this is an example about how we can use by combining two patents. And as I mentioned, there are some other applications. For example, we can use the algorithm to rank the exceptionality of a patent. So within this field, we use the guiding theory of the creativity philosophy, which talk about how to measure the creativity level of any artificial artifact. So, this, generally speaking, this philosopher has the idea that we can the creativity is nothing but the structured way of doing things, and for machine, and we can easily translate this idea into machine learning algorithm. So any kind of object, you can simply think this as certain projection in the vector space. And based on this, we can measure the three types of creativity. The first kind of creativity is a combinational creativity. Those are the things are created by combining the existing concept. We have exploratory, which are things that are explored within the given vector space, and we have transformational creativity, which is something that cannot be generated within the vector space, and that usually involve the creation of different dimensions. So we operationalize this philosophical idea, and we plot the three types of innovation across the time. Some of the research some of the finding we find is that we find the combinational innovation experience a stable exponential growth over time. We also find the innovation that's more exceptional are remain steady over the years. And generally speaking, the creative ideas are getting relatively more scarce over time. As I mentioned, with this tool, we can also explore the firm innovation according to their innovation patents. So here is an example about ranking the firm's innovation level by specific factors. So in this slide, I randomly select the 5 interesting technological factors: HCI, automation control, finance and connectivity. And in each factor, we find the 3 most innovative firms. For example, in HCI, we find that Nintendo, Pixar, and Emerson are the top player. And the automation and control, we found Intertrust, Silicon Motion, and Toyota to be the top player. And another thing is that we can not only rank the exceptionality, we can also synthesize new pattern by simply looking at the position of the firm's patent in the innovation space. So here's what we do. We just grab a bunch of Google's patents when we compute the center point of their core, and we through that point into the decoder and use that to generate the most representative firm of Google, for example. And we can see for Google, it's a pattern that's more talking about the secure documents, and for Microsoft, it's usually something talking about the computer system that has a screen and keyboard. And for the Apple, it's talking about the concept that is closely related to the user interface. So the generated text quality here is not very perfect because we're using like GPT-2, which is which has a very limited number of parameters. But you get the idea. We also have the firm for the representative pattern for Samsung, Adobe, and Ford, and all this generated the results and march our impression with these firms. Another example about this is that we can actually use this algorithm for some sort of decision support. For example, let's say there's recently the rumor that Google and Apple they are looking into the market of automation of the automobile making cars. And we can find, so what we do here is that we take the incumbent firms from this market space and we find the entrant firms, Google, Apple, and we compare their exceptionality within each factor and then find the top factors. And from this table, we can find out if Google and Apple want to compete with Toyota, they need to invest more automation and manufacture, and also maybe on a little bit about the connectivity within the automobile system. And similarly, we do the similar visualization for healthcare markets. And then here's the results. Another downstream, we also run some sort of kind of robustness check to see if our measured representation can be used for like a prediction. So we use this for predicting the firm market value, and we also use the Sharpe value to compare their strengths, the signal strengths compared to the traditional values, and the results show that our engineered variable that is really on par with the existing ones in terms of prediction. And nowadays there are many companies that's using the user-generated view to design products. So for example, there's recently this firm, the CNA Marketing, they have an entire team of people who read the reviews and trying to find a combinational innovation, a combinational product that's combined the two existing products. And I think this kind of thing is so this company are doing this manually, but I think with our algorithm, what can we do is that we can create the combinational innovation by using a machine, and this would be very scalable. And so we can also explore things in other spaces like product and jobs, etc., etc. So I think there's a lot of potential by having a generative algorithm that also have an interpretable representation space. Yeah, thank you.